Swayam Prabha. Digital India. Educated India.
Okay, so we'll talk about we start the generic attack. So far we have discussed the non-generic attack, where we don't care about the inner design of the cipher, but now here we will really look at the design of the cipher, and we will try to find out some flaw there or anything. So whether there is a linear attack is linear relationship. So this is basically non-generic attack. So this is basically all comes under non-generic attack. So in the non-generic attack, we look into the design of the cipher, and then we will try to find out whether there is any flaw or not. If there is any really linear relationship between the plain text and the ciphertext, those are linear attack. So non-generic attack are basically linear attack, linear cryptanalysis. We will talk about those. Differential cryptanalysis, differential attack, and some version of the differential attack like boomerang attack, impossible differential attack, truncated differential attack, and also the non-generic attack, slide attack or slide. So these are basically attacks on block cipher, but this can be extended to the stream cipher also. In some of the attacks we can think for. Then the related key attack. So this related key attack means we want to see whether is there any relation between the round keys. So this is the attack where we look into the key scheduling algorithm, the related key attack. Okay, like this. So these are basically non-generic attack. That means this attack is particular to that design. So we are looking into that particular block cipher, we are going into that design, and we are checking is there any flaw there or not. So then if we get something flaw, then we can attack it. Okay. So let us start with the differential attack, which is a non-generic attack. So differential attack was introduced for block cipher. So it is to find out the rth round key of the block cipher, differential attack on block cipher. So let us just recall what is a block cipher. So L bit block cipher means so it is basically a function which is taking L bit input, plain text, and this is the plain text, and this is the ciphertext, and it is taking the secret key k. This is the encryption, and decryption is the other way around. So it is a L bit block cipher. Okay, and for R round, if it R round, then there are R many round function is there. So suppose we have R round block cipher. R round means we have many R round function, f1, f2, dot fr minus 1, and last round is fr. So this is the plain text, which is the input of the first round. This is L bit, and this is the ciphertext, which is the ciphertext, which is the output of the last round or rth round. This is the R round block cipher, and we know this round function, each round function we need a round key. So where from we can get the round key? Round keys are coming from the algorithm which is called key scheduling algorithm. Key scheduling, which is a public algorithm, which is taking the secret key k, which is shared between Alice and Bob, and it is generating the round keys k1. For each round we need a round keys dot. So this is KR minus 1, and for last round this is KR. So, this is basically a typical R round block cipher. This is a typical R round block cipher, I mean L bit, if plain text hypertext are L bit. Now, this in the differential attack, this attack will be try to get the rth round key. So, this is the attack where we try to the attacker is attempting to find out the rth round key. So, for that we need to have something called differential trials. So, like if we take this, say these are the R rounds. So, just let me okay. So, this is the R round. So, suppose we denote this up to R minus 1 round as f function, capital F function, and this is the rth round, this is having a KR. So, this is the ciphertext. So, basically we have a f function which is taking input as a plain text and followed by a last round FR, and we got a ciphertext. Okay, and this is the, so this up to this R minus 1 round we call this function as f function. So, basically f is consist of f1 f2 up to fr minus 1. Okay. Now, we want to see some character, some existence of some differential trial in the this function or not, f function. So, for that let us define what is the differential trial. So, f is a function. So, suppose it is L bit. So, f is taking L bit input to L bit output. We have the round keys inside, that we are not bothering now. So, we are only concerned about this input, this output. So, f is a function. So, this is f function. Okay. Now, suppose we define the difference between this input. Suppose we take 2 x1 and x2, 2 input in f, and we XOR it. So, this is alpha. These are basically binary bits. So, this XOR is basically bitwise XOR. So, we just do the bitwise XORing. So, if it is 64 bit, say for DS it is 64 bit. So, x1 is 64 bit number 1 1, some 64 bit 0 1 bit, x2 is say 1 0 1 1 like this, 0 1 1 like this. So, this XOR means bitwise XOR. So, this is basically 0, this is no carry. So, this is 1, this is 1 like this. So, bitwise XOR, we take the difference. If the input difference is alpha in f only, then we want to see what is the output difference. So, this is basically y1 is basically f of x1 and y2 is basically f of x2. Okay, and we just do the XOR if it is beta. Then we say alpha is going to beta. So, this is called differential tail. We say alpha is going to beta. So, that means if the input difference is alpha, then we are getting the output difference beta. Okay. Now, if this alpha beta exists, that means with high probability, that means if you take input difference alpha, then with probability more than half, the output difference should be beta. So, if alpha beta is also 64 bit for DES. So, now if such alpha beta exists, then only we can mount the differential cryptanalysis, differential attack on this block cipher. So, so suppose such alpha beta exists with the high probability, that means if the input difference is alpha, then the output difference will be beta. So, for this f, this is f. So, if the input difference is alpha, then the output difference will be beta. So, that means with high probability. How to get this? We will come to an example with high probability means greater than half. This is a probabilistic attack, high probability. So, that means if you take input difference alpha, if you take 2 x1 x2 such that x1 x2 is alpha, then it is expected that they are y1 y2, y1 is basically f of x1, y2 is basically will be beta. It is expected, that means with that high probability this will be beta. So, this is basically we can say alpha is going to beta. So, suppose such alpha beta exist, then only we can mount the differential attack on this block cipher. So, suppose such alpha beta exist, then only one can we can mount the differential attack on this block cipher. How to attack? We will come to that. If such alpha beta exists, otherwise we cannot have the differential attack. If there is no such alpha beta with high probability, if we cannot find out alpha beta, then sorry boss, there is no, I mean this cipher is secured under differential cryptanalysis. Okay, like AES is secured, full round AES is secured under differential cryptanalysis, but DS is broken by the differential attack. Anyway, so now suppose we have such alpha beta, then how we can have a attack on this block cipher to find out rth round. So, that we have to, that is the exact attack on the rth round, finding the rth round key. So, differential attack okay. So, this is our block cipher F followed by a last round FR, which is taking the rth round key, and this is the ciphertext. And we know that alpha beta pair exist. We know this alpha beta, if the input difference is alpha, then the output difference of f will be beta with high probability. This exists, otherwise we cannot have this attack with high or significant probability. So, this is a probabilistic attack, otherwise no, sorry boss, this cipher is secured under differential cryptanalysis. Okay, so now how to attack this, how to get this clear? Suppose this alpha beta exists. So, what we do? We take two pair x1 x2 whose difference is alpha. So, that means we choose x1 equal to x and x2 is equal to x XOR alpha. So, if we choose like this, then x1 XOR x2 is basically x XOR x XOR alpha. So, this is basically x XOR x XOR alpha. So, this is cancelling out, this is alpha. So, if we choose these two x1 x2 this like this, x is a plain text, any plain text. So, x is, so if it is L bit, x is any L bit. So, there are 2 to the power L possibilities of x. Okay. So, there are 2 to the power L possibilities of x. So, what we do? So, we got a x, we choose a x, this choice can be done 2 to the power LOS, and then corresponding x2 is fixed because we want this difference should be alpha. So, we have to take x XOR alpha as x2. Okay. So, now for this x1 x2, this is a chosen plain text attack. This differential attack is a chosen plain text attack. We are choosing the plain text so that we can get the corresponding ciphertext. So, we choose these two plain texts. So, under this chosen plain text attack, we should get the corresponding ciphertext C1 and C2. So, C1 is basically encryption of x1 and C2 is basically encryption of x2, the plain text x1 x2. Okay. So, now we know the difference is input difference is alpha, we know the output difference of f will be beta, but we are here. So, how to go here? So, we know this difference is alpha. So, here f of, so basically we know this f of x1 if we denote by y1 and f of x2 if we denote by y2, we know this y1 x or y2 is beta most likely, because this is the high probability. So, this fact is known to us, we want to make use of this fact to guess what is KR. So, what we do, we can have the exhaustive brute force attack on this KR, exhaustive search. So, KR we can take, so if all the possible values of KR, so K1, okay, KR1, KR2 like this. So, if KR is KRN. So, all possible values, if n is, if KR is say for DES it is how many bits, round keys is 48 bits. So, for DES it is 48 bits, KR is 48. So, n is 2 to the power 48 for DES. So, this is all possible KRs. So, now we initialize down, this is a counter, we put the counter, initialize the counter by 0. Now, what we do? We choose a plain text and we get x1, we get corresponding x2, we got C1, C2. Now, we choose a candidate, we choose a KRI which is initialized by 0. This we will try for all possible KIs. Now, with this KRI we will convert this. So, with this KRI we will just apply Fi inverse KRI, sorry, KRI with this C1, we get some Y1 and Fr inverse KRI C2, we got some Y2. Now, we try this, we look Y1 XOR Y2 and we check whether this is beta or not. If this is the correct key, if KRI is the correct key, then it should give us here the difference beta, because this is the ciphertext, we are just want to, we have to reach here in order to get beta, because beta is the, if the input difference alpha here, beta is the output difference on F. So, we have to reach here, we need to know this KR. So, we are guessing this, we are taking KR is equal to KRI as a candidate key. So, if it is giving us beta, if it is beta, then we increase this KR by counter by +1. Okay. We increase this counter by +1 and this we will do for all possible plain text. We take another plain text as x1, then we choose corresponding x2 and this we are trying for all possible KIs. So, this way we compute this table and after completing this table whose frequency is more, then that is the KR. So, that is the attack. So, that is the corresponding rth round key. So, this is the brute force way, but this will give us the rth round key. Is this attack clear? So, this we have to try for, we choose a x from plain text, that is x1, x2 we get as XORing this. Now, we are here, now we choose all possible KIs and we invert this and we increase that this frequency by 1. If the corresponding KIs for that corresponding KI, we get beta over here, because beta is expected, because if the input difference is alpha, beta will be the output difference in F. Okay. So, that is expected. So, if we get beta here, then corresponding candidate key we increase the frequency. So, this we will do for all possible plain text, and then finally after doing this, finally we got this table with many values. So, finally the value which is having more frequency is the rth round key. Okay. This is basically the differential cryptanalysis on this block cipher to find the rth round key. So now the question is this attack clear? So this is the differential attack. Now the question is how we can find out such alpha and beta. So for that, let us just look at some simple block cipher to find the alpha beta. Maybe we can try for S box. So suppose we have a simple block cipher, like we have a S box 4 bit to 4 bit, like SPN S box. So S box is, this is say 4 bit to 4 bit X box. Okay, and we have a round key over here, XORing. This is the round key, simple block cipher. This is again 4 bit. Okay, now this is our F, say. Now we want to find out alpha beta for this S box. We want to find out alpha beta. That means if the input difference is alpha, then output difference will be beta for this S box. So this we want to see how we can get this alpha beta pair for this. This is a simple example to get alpha beta, but this may not be so simple function. It could be any f function. So only thing, we need to have a alpha beta in order to attack this block cipher by differential attack. Okay. So suppose you can take this S box as a SPN S box. So we have seen the SPN S box. So suppose this is a 4 bit to 4 bit. So we can just write this S box function like this. So 4 bit can be written as hexadecimal form 0 to f. So like 0, 1, this is the input, 0, 1, 2, 3 up to 9, then 10 is basically a dot 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 f. So f is 15. So 0 to 15 basically. Okay. Then the corresponding output we can have. We can take a standard S box, SPN S box from the book. So I can't remember the exact form of this. Suppose this is say 3 a 4 like this. Suppose we have this data. Okay. Now how to get this alpha beta pair? So what we can do? So this is the S box. So input difference will be, we want alpha, and the output difference will be beta. So you want such alpha beta pair. So what I can do? We can have a table like frequency table. So alpha beta is also 4 bit 4 bit. So what we can do? We can write this 4 bit as hexadecimal form. So alpha beta is also starting from 0, 1 to f. So beta is also starting from 0, 1 to f. Okay. So now what we do? We take a alpha beta. Say we are choosing alpha is equal to say 4, and say beta is equal to say we are choosing a. So this is say 4, and this is say a. Now we want to fill up this table. Like this table is a frequency table basically. So how to fill up this table? So for this 4 and 3, what we do? So what we do? We take so the possible beta is basically, so the input difference is 4. So input difference is 4 means we choose a x from this is our x1, and we choose x2 is x1 XOR alpha for a fixed alpha. Here it is 4. Then their difference is basically alpha. Okay. Now what we do? We compute this S box. So we compute y. So we compute y1 is basically f of x1, and y2 is basically f of x2. So here it is, f function is just S box. So we compute x1 XOR x2. So if it is, so it has some value. So say beta. So we add. So we have a. So basically we have a table like this for this alpha. So we have a beta value for a fixed alpha. So this is 0, 1, 2, like f. So, we initialize this by all by 0 count, this is just a count. So, this beta, so suppose this is say we are getting say b, so say here is b, so it was 0, so we add just plus 1 here if we are getting b. So, like this we change another plain text x, so alpha is fixed, so this is for a fixed alpha. So, alpha is fixed. So, for a fixed alpha we compute all these betas and we just add the count if we get that beta. So, we are varying this over the plain text. So, this way we can fill this table, frequency table. So, after getting this table who is having the maximum value, so that count we are putting here. So, that is the frequency having maximum value, this is f alpha beta. So, like this we compute this table for all possible alphas. So, if we take another alpha we will do having same technique, we will choose a plain text x1 then x2, we compute this and the maximum frequency we store it here. So, this table we can compute. So, in this table if all the values are almost same, then there is no differential tail exist, but if there is a value say all are say 10 and if there is a value say 112 frequency, then the corresponding alpha beta is our differential tail, then we can mount the attack if such exist. This is the frequency table. So, that means there is a significant probability that if we take input difference alpha, then the output difference will be beta. Okay. So, this is the way we can find alpha beta, but if such alpha beta exists, then only we can mount the differential attack, otherwise not. So, this table can give us the such alpha beta. If all the values of these tables are similar, then there is no such alpha beta exist in the f. So, this block cipher is cannot be attacked by the differential cryptanalysis. Okay. So, I suggest you can just have a try to get this alpha beta for the SPN network, which we have discussed in our block cipher. So, just try to get some alpha beta for that, whether such alpha beta exists or not. Thank you.